So this lecture is really just more of an in-depth review of some of the concepts that you guys learned in your Engineering 120 series. All we're going to do today is talk about the concepts of current, voltage, power, and energy. Okay, I'm going to throw charge in there as well. Let's start with voltage, because it is likely the quantity that you're most familiar with. Okay. And I'm going to start with a mathematical definition that we will never actually apply, okay? So our mathematical definition for voltage, VBA, is equal to the integral from A to B of our electric field vector, E, dotted into some differential line element, DL. We're not actually going to use this, just to be super clear, okay? What this thing says is that voltage depends on 2 points, right? So we have E dotted into DL, okay? That's a line integral. A line integral effectively means that we're going to get some number when we integrate from some point A to some point B. And if we're dealing with a conservative force, which we absolutely are, it doesn't matter what path we are going to take, okay? I'm going to break this integral up a little bit more by throwing even more math that you really don't need into this, because most of you haven't had electrical field theory, okay? So the electrostatic force, F sub E, is equal to charge times electric field. This is commonly called Coulomb's law. And we can rearrange this to say that our electric field vector E is simply 1 over charge times our force. I'm going to substitute that relationship up into the previous equation. And since charge does not depend on position, that 1 over Q term is going to come outside of the integral. So I'm going to have voltage is equal to 1 over Q times the integral from A to B of F dot DL. What's the integral of F dot DL? What? Force times distance is what? Work. That's what that integral is. Voltage is nothing more than the amount of work it takes to move charge from one point to another in a circuit per unit charge. That is all that voltage is. Okay. So work or energy per unit charge needed to move 1 Coulomb of charge between 2 points in a circuit. Okay. My units of voltage are very easy to determine from this equation as well, because I know that that whole integral is work or energy measured in joules, and charge is measured in coulombs. So I have 1 over coulombs times joules, or joules per coulomb, is my fundamental unit of voltage, right? So 1 joule per coulomb is equal to 1 volt, V, and this is our unit of voltage. Very easy to remember. Okay. Because we're dealing with a line integral, we can actually come up with a second, I would argue, more useful definition for voltage for this class, okay? So voltage is a measure of electrical potential energy, okay, between 2 points. So what do we know about another form of potential energy? Gravity is a form of potential energy, right? So if I take this marker and I lay it on the surface of this table, it has some amount of potential energy. And if I move it up some height, it has a different amount of potential energy because of that height difference. It does not matter if it's this height over here or this height over here, as long as it's the same distance away from the surface of the desk, it has the same amount of potential energy. Voltage is the exact same thing, except it's electric potential. It is path independent. So another way to express voltage is the difference, go away menu, in electrical potential energy between 2 points in a circuit. So these two definitions really tell us two different things about voltage. The first one, work per unit charge needed to move things, explains why voltages are necessary to cause currents to flow, because we need a voltage to push charge around a circuit, okay? The second definition is related to how we measure it. It's just a difference in electrical potential between 2 points in a circuit. So we can use a multimeter between 2 points in a circuit and observe a voltage, okay? So this second definition is the one that we are going to use most often in this class, okay? So let's talk about how we define voltages, okay? So I'm going to draw a generic circuit element. And let's call this element A. And I'm going to say arbitrarily that the voltage VA, so the voltage drop across this element A, is 5 volts. This is an incomplete representation of voltage, okay? So in this class, when we express voltages, voltages are going to have both a magnitude, which is what we've taken care of right here, but they are also going to have a polarity, okay? So I am arbitrarily going to choose the positive polarity terminal to be on top and the negative polarity terminal to be on bottom. What this means is that the positive polarity terminal is at an electric potential that is 5 volts higher than the negative polarity terminal, okay? So if you guys happen to have a AA battery or anything like that in your pocket, probably not, but you could always look up a picture of one on your phone, they explicitly have positive and negative polarity terminals labeled. What's the voltage of a AA battery? 1.5 volts. So literally all that means is that the positive polarity terminal is nominally 1.5 volts higher in potential than the negative polarity terminal. Doesn't tell you what the potential of the negative polarity terminal is, doesn't tell you what the absolute potential at the positive polarity terminal is. It's just the difference between those two terminals, which is exactly what we're representing here. Okay. So how many of you guys using your multimeter ever measured a negative voltage in your engineering 120 classes or anything like that? Probably a lot of you guys. What did you do to fix that negative voltage? Swapped it. So that's exactly what we're going to do here, right? Anytime we observe a negative voltage, so I could say this is negative 5 volts with the opposite polarity, and it represents literally the exact same thing. So anytime I want to get rid of a negative sign for a voltage, I can do that by changing the polarity of my terminals. So this method of identifying voltages is the American style. Okay. So here in the United States, for the most part, we use magnitude and then a positive polarity terminal and a negative polarity terminal. So now, just because I know that some of you are going to watch YouTube videos to figure stuff out because you're just not going to be on board with the way that I'm teaching things, that's perfectly okay. A lot of those YouTube videos are going to be from not in the United States. So let's talk about another different way that you might see voltage represented in a circuit. Okay. So we have our same generic circuit element A. We have the same magnitude of 5 volts, but in the European style, they represent their polarity with an arrow, where the head of the arrow is the positive polarity terminal, and the tail of the arrow is the negative polarity terminal. I personally do not care for this because to me, arrows are associated with currents. Okay, so I don't particularly care for this way, but it is something that you will absolutely see or could potentially see, depending on, you're watching YouTube videos, reading textbooks from outside of this country, all that kind of good stuff. We could represent negative 5 volts by just having an arrow in the opposite direction. So this is the European style. Other than exactly right now, you will never see me do this again. Okay. And then there's a third style that we're going to use effectively a modified version of it in this class when we start talking about nodal analysis. Okay. So I'm going to draw that same element. Now I'm not going to call it element A though. What I'm going to do is I'm going to label my terminals, A and B. And this is what's called double subscript notation. Okay. So for this particular setup, I would have a mathematical statement like VBA is equal to 5 volts, where the first letter in the subscript corresponds to the positive polarity terminal, and the second letter in the subscript corresponds to the negative polarity terminal. Okay. So from that, I could say that VAB would be negative 5 volts. So if I flip the order of the subscripts, I'm flipping the polarity of the terminals. Okay. Not going to be used a lot in this class, but it will be a little bit of a thing for those of you that go into circuits 2 and all that kind of stuff. We're going to use it extensively dealing with multi-phase power systems, just because there's going to be so many nodes that have specific meanings that this is the easiest way to figure out where we're measuring voltages between and all that kind of good stuff. Okay. So these are the 3 different ways that we represent voltages on our schematic diagrams that we're going to be working in this class. The overwhelming majority of the time, this is the way that we're going to do things. Okay. So just to reiterate on this particular one, in the American style, we have a magnitude, so some number of volts, and then we also have a polarity indicated by a positive polarity terminal on one leg of our element and a negative polarity terminal on the other leg of our element. If we ever have a negative magnitude, we can get rid of that negative magnitude by simply swapping the polarities of our terminals. Okay. All right, so we've talked about what voltage is. We've talked about how we're going to represent it on circuits. Now let's talk about the different voltage sources that we are going to see in this class. So the first one that I'm going to draw over here on the left is the humble battery, which is what you guys have seen in your previous classes. This is the typical symbol for a battery. I prefer explicitly giving it a positive and negative polarity terminal. The long line is always the positive polarity terminal, and the short line is always the negative polarity terminal for a battery schematic symbol like this, but I prefer to explicitly write it so that there is no confusion. In fact, I don't actually like to use the battery symbol at all, because we deal with capacitors in this class, and capacitors equivalent, excuse me, the capacitor representation for a schematic is something very similar to this, except the two lines are of the same, two parallel lines are of the same length. And if you're not careful when you're drawing things, you can get lazy and your capacitors can look like batteries and vice versa. So while this is what you are familiar with to this point, it's not what we're going to use for the most part. Instead, we are going to use this symbol. And let me just put here VS for the magnitude of the voltage. Okay. So this is a generic DC voltage source. So the magnitude of the voltage that's being supplied by this source is whatever VS happens to be. And there is a plus and minus sign indicating which terminal is the positive polarity terminal and which terminal is the negative polarity terminal. So all of the information is buried in the symbol itself with regard to polarity. Okay. A little bit later in the class, we are going to look at AC voltage sources. Okay. Exact same symbol as our DC voltage source, except that there's a little squiggle in the middle, and that squiggle tells us effectively that the voltage is changing in time. Okay, so here's another thing that I do. Doesn't show up in a lot of your homework problems, which I think is dumb, but whatever. I represent DC quantities with capital letters, and I represent AC quantities with lowercase letters. So since this is a time varying voltage source, I would call this lowercase VS, and I would typically also say in parentheses T to let you know that voltage is dependent on time. Okay. These three voltage sources are what are known as independent voltage sources. So they are independent voltage sources because they supply a fixed amount of voltage regardless of what they are connected to, right? So if I have a battery in my hand, without anything attached to it, it's still providing 1.5 volts of electric potential, okay? Does not matter if I put a resistor across it, a capacitor, inductor, it's going to supply 5 volts, okay? So independent voltage sources means that there is a potential difference between those terminals of VS regardless of what is going on in the circuit. Over here on the right, we're going to introduce dependent voltage sources, okay? I'm going to draw both of these symbols right now. They are going to be identical. And the nuance will come from the magnitude, okay? So on the left-hand side, I'm going to call this a voltage controlled voltage source. And on the right-hand side, this is going to be a current controlled voltage source, excuse me. And these are both examples of dependent voltage sources. So now let's talk about the magnitudes here, right? The polarities are identified by the positive polarity sign plus and the negative polarity sign minus. So all of that is taken care of. So how we can tell the difference between these things is actually in the magnitude. So for a voltage controlled voltage source, we're going to have K times Vx, okay? So this voltage Vx is the voltage that controls the voltage source, and K is some scaling factor. So this voltage source is going to supply K times Vx amount of voltage, okay? K here is a unitless quantity, or we could think of it as volts per volt, okay? So it's converting some voltage elsewhere in the circuit into the voltage that is being supplied by this particular element. In contrast, our current controlled voltage source, let's see, so I'm going to have volts per amp, is going to be R times Ix, where this scaling factor R has units of volts per amp. So my current controlled voltage source takes a current from somewhere else in the circuit and converts it into a voltage by multiplying that factor R by that controlling current Ix, okay? These right now may seem like magical, weird things. We actually use them all of the time because almost all of the electronics that we have in our pockets and stuff like that are based on transistors. And this is part of how transistors do their jobs, okay? So we're not going to go into a lot of the nitty gritty of these, but they are going to show up a lot, I think, even on your first little homework assignment and all that kind of stuff. They can seem confusing and daunting at first, so I am more than happy to entertain questions about them now and throughout the class, just when something doesn't make sense, because this is, these dependent sources are a concept that students kind of get confused on pretty regularly, sometimes for the whole damn quarter, okay? So if you ever have any questions about why is it this way, by all means ask, okay? So these are the 5 different types of voltage sources that we might see. So we've talked about what voltage is. We've talked about how we represent voltages on circuits, and we've talked about the different elements that we are going to see that provide voltage to circuits. Does anybody have any questions about voltage in general before we move along and talk about current? All righty. So now we're going to talk about current. Okay, so let's start with a mathematical definition. Current, I of t, will be the derivative of Q of t with respect to time. So this I of t is current. And this Q of t is charge. Okay. So this is our mathematical relationship for current. We're absolutely going to use this one. We're not going to use that fancy line integral and all that kind of stuff for voltage, but this guy is going to come into use. Okay. So our unit of current is simply the unit of charge. So a coulomb divided by the unit of time, seconds, and we call this an ampere or an amp. So since current is simply the derivative of charge with respect to time, what would be a simple definition that we could describe current as? So whenever we take the derivative, what are we doing? We're looking at a rate, right? So if we have a displacement x and we take the derivative of x with respect to time, we get a velocity, which is the rate at which we move, or the rate at which the displacement changes, right? So current is nothing more than the rate at which charge moves through a circuit. Some number of coulombs of charge in some amount of time gives us a current, okay? And before I forget about it, we are going to manipulate this expression to get an equation for charge as a function of current, okay? So if I multiply both sides by dt, and then I take the integral of both sides of this expression, what I'm going to wind up getting is q of t, my charge, is equal to the integral of I of t dt. And now we're going to have to play around with things a little bit here. So I'm going to put some limits on this integral because we're engineers and we like numbers. I'm going to start my integration from t naught, okay? So t naught represents some time at which q is known. I'm going to integrate t, some later point in time that we're trying to figure out what the charge is. Now, in mathematical speak here, I have a little bit of a problem because t is in my limits of integration, but it's also my variable that I'm integrating with respect to, okay? So I am going to use a dummy variable, and I'm going to indicate that by simply putting a prime on the t's inside my integral, okay? So I want to be very, very clear here. This prime notation does not mean take the derivative of this with respect to time, which is a notation that is often used, okay? This is literally just, I can't have the same letter inside my integral as I have in the limits of my integral, or it gets wonky. That's it, okay? In other math classes and all that kind of stuff, you might use the Greek letter for t, which would be tau, but in electrical engineering, tau has a very special meaning. It is a time constant for exponentially decaying circuits, so we can't use that letter. So I'm using t prime just as a dummy variable. You could use x or r or any other dumb letter you choose. As long as you remember that it represents time, you're all good. And now we need to add one other thing here. Q of t. This bit on the right-hand side is the initial condition on the system, right? So this is the known amount of charge, Q, that's referenced in the definition of T naught, okay? So we are saying effectively that in order for us to determine charge from current, we have to have some memory of how much charge was stored to begin with. That's all this thing really states, right? The units of charge are the coulomb. See? No definition from other units. This is a fundamental unit. Okay. So just so we're clear about how to apply this second equation, I think we're all pretty good at probably just taking a simple derivative at this point. Let's take a look at this equation here. So let's say that I have the following current waveform. Let's call this 8 amps. Let's call this 2 seconds. And 7 seconds. And let's say, just for the sake of argument, we want to know what Q is at this point, which would be 4.5 seconds with the initial condition that Q of 0 is, and since I'm making this up, these units might not come out to be super great. Let's see. Seconds. 3 coulombs. So how can we apply the equation that I've developed above? There's really 2 ways that we could do things here, right? So if I'm looking for, so let me write this down explicitly. This is a quantity that I'm trying to find. I have a piecewise function that I could mathematically define using my knowledge of math, and then I could literally take the integral of that piecewise function, right? That could be a thing. What's another way we could use? Area under the curve, which in this case is just triangles and rectangles. For the most part, in this class, the only calculus that I'm going to ask you guys to do is derivatives and integrals of exponential functions, derivatives and integrals of sinusoidal functions, and derivatives and integrals of simple like t cubed and things like that, like very simple polynomial functions, okay? Nothing wild or crazy. If I give you a graph, 99% of the time, my expectation is that you're going to be able to just look at the damn thing and figure out the area under the curve using the area of a right triangle and the area of squares and rectangles, okay? So for this particular problem, let's use area of triangle, area of rectangle, and figure out what the results are going to be, because it'll take 10 minutes to do it the other way, okay? So I'm going to ask you guys what I sincerely hope is a trivial question. What is the area of this triangle? Eight what? 8 amp seconds, okay? So I'm going to ask a slightly, an even dumber question. How did you get the area of the triangle? Thank goodness. Okay, now I'm saying that sincerely. I taught this class one summer to about 20 students, and I am not kidding you that over 8 of them did not know how to get the area of a right triangle. Okay, so I am so thankful that at least some of you are willing to state out loud that the area of a right triangle is 1/2 the base times the height. So that's going to be 1/2 2 seconds times 8 amps comes out to be 8 amp seconds, where an amp times a second is a coulomb. What's the area of this rectangle? 2.25 times 8, right? So just the base times the height, no factor of 1/2. So to be even more explicit here, 4.5 seconds minus 2 seconds, so 2.25 seconds times 8 amps. So let's see, 2.25 times 8, that's 20. Or excuse me, 2.5. Yeah, well, 2.5 times 8 is the thing that equals 20 anyway, so, but you're right. 20 coulombs. Okay, everything's hunky-dory there. So how do we figure out what Q at 4.5 seconds is? And then also the initial condition. That's absolutely right. So it's not just going to be 28 coulombs, it's going to be 31 coulombs, because we have to take into account that there were 3 coulombs of charge at T is equal to 0. 100%. Great job. You guys did trivial math. Wonderful. Genuinely wonderful. All right. So we've talked about the relationships between current and charge. We've worked a simple example problem here that is literally representative of what might show up on your exam, kind of thing. Nothing terribly wild here. So now let's talk about how we represent currents in circuit diagrams. Okay. So let's say that I have generic circuit element A. And let's say that the current IA is equal to 2 amps. Once again, this is underspecified here, okay? I have a magnitude, but currents also have a direction, and the direction is very important. So we indicate the direction of a current by simply putting an arrow. So if I have 2 amps down, that is going to be the same thing as negative 2 amps up. Okay, so I can get rid of a negative sign on a current by changing the current's direction. Okay, this is the only way we're going to represent currents in this class. So we're just going to stop here and call it a day. Okay, so when I want to represent a current in a circuit diagram, I give it a magnitude, some number of amps, and I also have to give it a direction. The direction is critically important. We'll see in a few moments. So now let's talk about the various types of, yes. What do you mean by that specifically? Okay, so fantastic question. All right, so I understand you a little bit more here. Yeah, so we are working with conventional current where we are under the erroneous assumption that positive charge is moving around. But you are absolutely correct that currents are caused by the movement of electrons, and electron movement is actually in the opposite direction of what we would call a positive current in this class, because electrons have negative charge. So this comes about from the fact that electrons weren't discovered until actually the late 1800s, where we theorized them. I think we observed them in 1922, but Ben Franklin's dumbass way back in the 1770s said, there's an electric fluid and it behaves this way without understanding anything, and effectively got the direction wrong. So you're 100% correct. We are going to be dealing with conventional current, so the movement of positive charge carriers. Yeah. All right. Current sources. That's what we're talking about. So there are going to be a few different current sources that we are going to encounter in this class. This is our DC current source. So we have some amount of current being supplied. So our magnitude is IS, and then the direction of the arrow in the middle of this thing tells us what direction the current is flowing. Here is our symbol for our AC current source. It's just the DC current source symbol with a squiggle in the middle to let us know that we have a time varying current. So our magnitude would be IS of T, lowercase, because we're dealing with time varying quantities. And these are both examples of independent sources. Over here on the right, I'm going to draw our dependent current sources. So let's call this one on the left a current controlled current source. And this one on the right will be a voltage controlled current source. Which are examples of our dependent sources. Okay, so we've seen we've seen independent voltage sources. Now we've seen independent current sources. Generally speaking, if it's a circle, it's an independent source. Okay. Similarly, we've seen dependent voltage sources and dependent current sources. So if it's a diamond or rhombus or square turned on its side, however you choose to represent that shape in your head, we have a dependent source. Okay. Scrolling back up here really quickly. Voltage sources have plus and minus signs indicating positive and negative polarity terminals. Current sources have arrows indicating the direction of current flow. So that's how we're going to tell the difference between all of the different sources here. Okay. So a current controlled current source will have a magnitude of K times IX, where in this case, K, once again, a dimensionless quantity, will have units of amps per amp. And for our voltage controlled current source, we will have G times Vx, where G has units of amps per volt. All right, does anybody have any questions regarding current? All right, so now let's talk about power and energy. So mathematically, power P of T is the derivative of work or the derivative of energy. Okay. But I'm going to be fancy here and I'm going to split that derivative up. Okay. So I'm going to say that instead of it being the derivative of energy with respect to time, it's going to be the derivative of energy with respect to charge multiplied by the derivative of charge with respect to time. Energy over charge is nothing more than voltage. And charge over time is nothing more than current. So we simply have power is the product of voltage and current. Arguably using all those fancy pants relationships that we developed at the beginning of the class, instead of just telling you what the damn answer is, like what happened in engineering 120s, because I have to be fancy. All right, so this is our power relationship, the unit of power. So we can see pretty easily here that it's going to be 1 volt times an amp, which is the same as a joule over a second. And this is the watt. Our word definition of power is going to be the rate at which energy is transferred to or from a circuit element. And now we're going to define energy in terms of power, because everybody loves cyclical reasoning. Okay. So energy, W, is going to be the integral of the power from some point in time T1 to some other point in time T2. And we will define energy for the intents and purposes of this class to be the total amount of power transferred to or from, sorry, my penmanship is getting worse as the class goes on, a circuit element over a fixed time interval. All right, so I am about to introduce the concept of the passive sign convention, okay? This is something that I honestly do not understand why people are confused with, but they regularly get confused with this. To me, it is extraordinarily straightforward. I am going to explain it to you as simply as I possibly can, okay? And just as a heads up here, you will literally be asked questions about this little topic that we're covering on the second day of class on your final, your non-cumulative final. This is going to come up all the damn time, okay? So passive sign convention. Let's say that I have a generic circuit element A that is connected as some part of a larger circuit, where the rest of the larger circuit is being represented by these ellipses here, okay? So I just have a circuit element connected to other things. Let's say that we can measure a voltage drop across this circuit element, VA, positive polarity on top, negative polarity on bottom. We are making no assumptions whatsoever about what the sign of this voltage VA is. We are simply measuring it with positive polarity reference on top, negative polarity reference on bottom. If a current IA flows into the positive polarity terminal, then the power absorbed by element A is VA times IA. And the power supplied by element A is negative VA times IA. At no point have I mentioned signs on any of these quantities, okay? So I am simply saying when the current is flowing into the positive polarity terminal, the product of current and voltage gives us the absorbed power. That could be a positive quantity, it could be a negative quantity, but we are considering this element, this element to be absorbing power because current is flowing into the positive polarity terminal, okay? To get the supplied power, we simply change the sign. Now let's look at the opposite case. We have our generic circuit element A. We have some voltage drop VA across it. But now our current is flowing into the negative polarity term, right? My supplied power will now be VA times IA, and my absorbed power will be negative VA times IA. This is all the passive sign convention is. Doesn't have to be any harder than this, okay? So effectively, when the current is flowing through the positive polarity terminal, absorbed power is I times V. If the current is flowing into the negative polarity terminal, the supplied power is I times V. And if we want the opposite quantity, we just change the sign. That's it. Okay. Again, it doesn't have to be harder than that. You guys are going to be working your web work problems and all this, that, and the other. You're going to work a problem. You're going to be like, oh, the answer is, let's say 43 watts. And it's going to tell you you're wrong. And then you're going to blindly change the answer to negative 43 watts. And it's going to tell you that that answer is right. The reason that answer is right is because of the passive sign convention. And you just made a mistake with a sign somewhere. Okay. This is going to bite you in the butt for the next couple of weeks for sure, potentially all the way through the end of the quarter. Okay. If you have questions about it, I would be more than happy to talk about it. But for right now, I'm sure it seems real simple because it is. But once you're trying to put it into practice, hiccups and all that kind of stuff happen. I'm more than willing to work with you to figure things out there. Let me think here. All right, the last thing that I want to talk about is Telegen's theorem. Telegen's theorem simply states the sum of the powers in the circuit bag is 0. That's it. Okay. So watch. Let me look at your in-class assignment. Let's do this one. We're going to work problem 3 from your in-class assignment together. We are going to show how to use the passive sign convention to determine things. And we are also going to verify intelligence theorem while we're at it. Okay. All right, so we are asked to calculate the power that is absorbed by each of the elements in this circuit. So let's start with the 36-volt source. So what's the voltage drop across the 36-volt source? It's in the name, 36 volts. How much current is flowing through the 36-volt source? 4 amps. Is that current flowing into the positive polarity terminal of the 36-volt source or the negative polarity terminal of the 36-volt source? Since it's flowing into the negative polarity terminal, I times V is the supplied power. We want absorbed power, so we add a negative sign. And we get negative 144 watts. Let's look at element 1. What's the voltage drop across element 1? 12 volts. What's the current flowing through element 1? 4 amps. Is the current flowing through the positive polarity terminal or the negative polarity terminal of element 1? The positive polarity terminal. Since we are calculating absorbed power, we leave it alone. 12 times 4. 48. Look at element 2. So what's the voltage drop across element 2? 24 volts. What's the current flowing through element 2? 2 amps. Is the current flowing into the positive polarity terminal or the negative polarity terminal? The positive polarity terminal. So we get another 48 watts here, not 18 watts here. All right, let's look at the dependent source. So what's the voltage drop across the dependent source? What was that? 4 volts. Okay. Explain your reasoning. You're right, by the way. Right. Okay, so you're 100% correct there. It's 1 times Ix, and Ix is equal to 4 amps, so it's 1 times 4 amps. But how do we get volts out of that? Because the 1 has to have units of volts per amp, because this is a current controlled voltage source, right? So because there's a plus and a minus sign there, this is a voltage source, not a current source. I'm not going to explicitly give you the units of that scaling factor. The units have to be whatever they need to be to make that thing output a voltage, which in this case is volts per amps. Okay, so 1 volt per amp times 4 amps gives us 4 volts. So our voltage is 4 volts. How much current flows through it? 2 amps. Really, I should have drawn that 2 amp here, because while it should be intuitively obvious that there's this 2 amps, there's no opportunity for it to split off or branch or anything like that. So it has to be flowing up here as well. We technically have covered that because we haven't looked at Kirchhoff's current law. So a better way to represent it would have been up here. So our current flowing through our dependent source is 2 amps. Is the current flowing into the positive polarity terminal or the negative polarity terminal? It's flowing into the negative polarity terminal, which means 4 times 2 gives us our supplied power. Because we're calculating absorbed power, we need to throw a negative sign at it. So we get negative 8 watts. And lastly, we have element 3. What's the voltage drop across element 3? 28 volts. What's the current flowing through element 3? 2 amps. Is the current flowing into the positive polarity terminal or the negative polarity terminal? Into the positive, meaning we don't add a negative sign. And so we get 56 watts. If we add all of these powers up, what do we get? 0, because intelligence theory. All right, that's enough out of me for today. So we have a mini lab. Like I said, it's the assignment sheet for the mini lab is posted online. It's a fairly straightforward experiment, all that kind of stuff. It requires the use of 2 multimeters. Since most of you probably didn't pay attention to syllabus, it says that we have a lab today. There's a huge bin full of multimeters down here. You are going to be measuring a current. Okay, so that's critically important because if the fuse in your multimeter isn't working correctly, you're not going to be able to measure a current. So I know this is going to sound maybe dumb, but for each team, I would probably get 3 or 4 of those multimeters, if not more, because you're just going to have to find one where the students haven't blown the fuse out yet. If you didn't happen to bring your own. So yeah, so the mini lab assignment sheet is on Moodle, so you can print it out or just type into it as a PDF or whatever. There's also an in-class assignment to be working on, so do things.